Imagine taking the most hellish, inhospitable planet in our entire solar system and completely remaking it. I'm not talking about some slow geological timescale project. I'm talking about doing it in a single century. Well, today, we're diving into a genuinely audacious engineering proposal that lays out exactly how to do that. A 100-year plan to terraform Venus.
And believe me, when I say hellish, I am not exaggerating. Scientists don't mince words here. They call Venus the most hostile planetary environment that we know of, period. It's a world wrapped in a thick, toxic blanket of almost pure carbon dioxide that literally crushes and cooks anything that dares to touch its surface.
Okay, so let's really put that into perspective. Here on Earth, we enjoy a pretty comfortable average of 15 degrees Celsius and 1 bar of atmospheric pressure. Nice, right? Now on Venus, the average temperature is 450 degrees Celsius. That's hot enough to melt lead. And the surface pressure is over 90 times that of Earth's. To feel that kind of crushing force, you'd have to dive nearly a kilometer deep into our ocean.
Which, of course, brings us to the big question. When a planet is this far gone, when it's locked in this stable, brutal, runaway greenhouse effect, how do you even begin to fix it? Well, the answer is, you don't. You have to break it even more.
See, the strategy isn't to gently nudge Venus toward a better climate over a few millennia. No. The plan is to hit it, and hit it so hard and so strategically that its entire atmospheric system collapses into a new state. It's a radical, incredible idea called cascade engineering.
The core idea here is called cascade engineering. To get your head around this, stop thinking about Venus's atmosphere as just a gas. Instead, picture a giant, brittle glass dome. Now, you could spend forever trying to chip away at it piece by piece. Or you could find the perfect stress point, give it one coordinated hard shove, and watch the whole thing shatter. That lets you build something entirely new from the pieces. That's the goal here.
And this breaks it down perfectly. It's really a three-step process. First, you perturb this system. You give it an initial, powerful shock. Then you amplify that shock, using self-reinforcing feedback loops to make it grow and grow. And finally, those amplified effects trigger a total collapse of the old, stable, hot atmosphere. It's literally like tipping the first domino in a planet-sized chain reaction.
So you're probably wondering, what kind of crazy toolkit do you need to push an entire planet over the edge? Well, let me tell you, the tools are straight out of science fiction, but the physics behind them is surprisingly grounded in reality.
All right, tool number one. This is the big one. The primary catalyst, the engine that's going to drive this whole transformation, is a massive system of orbital mirrors. Their job is to create a planetary scale temperature difference, and the sheer scale of this is, well, it's just hard to wrap your head around.
And when I say massive, I'm not kidding. We are talking about 50,000 individual mirrors all working together in orbit. This isn't just one system either, it's two, working in perfect concert to create a planetary weather engine from scratch.
But here's where it gets really clever. These mirrors have a dual purpose. Part of the array acts as a giant sunshade, blocking sunlight to create a super cold pole where CO2 will literally freeze out of the air and fall like snow. At the same time, the other part acts like a magnifying glass, focusing sunlight on the opposite pole to create a super hot spot of 2,000 degrees Celsius. This insane temperature difference is what kicks the whole atmospheric cascade into high gear.
So the mirrors create this giant weather engine, right? But you still need something to kickstart it, a starter crank, if you will. And that's where our next tool comes in. And let me tell you, this plan's definition of a push is not subtle. We're talking about ultra-high-yield thermonuclear devices deployed on a scale that has never, ever been imagined before.
The plan calls for devices that scale all the way up to 1 teraton. Now, to put that number into perspective for you, that is the equivalent energy of the asteroid impact that wiped out the dinosaurs. But in this case, that extinction-level force is being repurposed for planetary construction.
So what does that even do? Well, the effect of one of these things going off in Venus's incredibly dense atmosphere is described perfectly here as creating scalable earthquakes in the air itself. The shock waves would be so unbelievably powerful they would ripple across entire hemispheres, creating just massive, sustained disruption in the atmosphere.
All right, on to our final major tool. This one is less about shocking the atmosphere and more about fundamentally changing the planet's surface chemistry. We're talking about a relentless, decades-long campaign of kinetic bombardment.
This means dropping 1 million, yes, 1 million, massive tungsten rods from orbit. Each one slams into the surface like a small bomb.
But their purpose isn't destruction. The impacts dig craters, exposing fresh, unweathered rock from below. This new rock is chemically hungry, and when it's exposed to the carbon dioxide atmosphere, it soaks it up, trapping it permanently as carbonate rock. You are literally turning the atmosphere into stone.
Okay, so we've got the mirrors, we've got the giant nukes, and we've got the impactors. That's our toolkit. Now let's look at the timeline. How do all these pieces come together over 100 years to take Venus from hell to, well, something new?
So, the first decade is all about construction, getting everything into place. But then, at year 10, bam! The first nuclear detonations kick off the cascade. By year 30, the atmosphere crosses a critical threshold and starts to actively transform itself. The campaign just escalates from there, and by year 80, the massive Keraton-scale events begin, creating those planet-spanning earthquakes in the air. By the end of the century, a new Venus is born.
So after a century of this controlled chaos, what does the new Venus actually look like? Well, this table shows the incredible transformation. The surface pressure is nearly cut in half. The average temperature has dropped by a staggering 130 degrees Celsius. And, for the first time in its history, the planet has permanent polar ice caps made of frozen carbon dioxide. It's not Earth yet, not by a long shot, but it is a fundamentally new world, broken free from its hellish equilibrium.
Now I know what you're thinking. An undertaking of this magnitude must have an absolutely astronomical price tag. So, what are we talking about here? What would something like this actually cost?
Okay, brace yourself. The total estimated cost is around $1 trillion. And I know, that sounds like an impossible number. But when you spread it out over 100 years and across the entire global economy, it actually comes out to about 0.1% of global GDP annually. Now, for comparison, at its peak, the Apollo program cost about 4% of just the US GDP. So, in relative terms, this planetary makeover is surprisingly feasible.
And all this incredible, world-breaking technology, it leaves us with one final, profound question. Because the plan, by all accounts, seems technically possible. The engineering is really just an extension of things we can already do. So we are forced to ask, just because we could develop the power to remake an entire world, does that mean we should? Now that's a question worth pondering.